Hello everyone, and welcome to a discussion of Projectile Motion Worksheet 2. So in this worksheet we were examining a ball launched horizontally off of a building. The building has a height of 90 meters and it's shot with a velocity of 25 meters per second. Now notice it's launched horizontally off that building is important at this point. So the first thing we have to do is to figure out all of our many variables. And it's important that we kind of list these out so that we can see what we have to work with. And there's lots of variables to work with in two-dimensional projectile motion. So let's start off with our horizontal ones. And here we have the initial horizontal position. Well, since really it's just wherever the top of the building is, you might as well just call that 0. Make your life easy. X is the final horizontal position. Well, we don't really know what that is. It depends, really, how much time has passed where we are. So that'll be a question mark. We do know the initial horizontal velocity, which is actually the horizontal velocity the entire time, since the horizontal velocity of a projectile is constant. And since it's shot horizontally at 25 meters per second, that's the horizontal velocity. As I just mentioned, the horizontal velocity is constant, therefore the horizontal acceleration is 0. Remember, there are no forces acting horizontally on a projectile. Time is kind of our variable that works both horizontally and vertically, and time is something we're not sure of at this point until we get to the next part. The vertical quantities, y sub o, this is your initial vertical position, or you could look at this as initial height. Well, since you're on top of a building that's 90 meters tall, it would be 90 meters. Your final height is something that we're not sure of. Your final vertical velocity, we're also not sure of. That would be the speed with which you hit the ground vertically. We could calculate that, but we certainly don't know it yet. Not something we can just read out of the problem. Your initial vertical velocity, however, we do know. Since you are shot horizontally, when something is horizontal, there is no vertical. So your initial vertical velocity is 0, and that's going to be important to working out the equations. And of course, as we showed both experimentally and theoretically, the vertical acceleration is little g, or negative 9.8 meters per second squared. Notice the negative because it's down. Now this is a process you're going to want to go through with pretty much all of your two-dimensional projectile motion problems. You may not draw out a chart like this, but you need to think through all of the different variables. Now the next part of the problem asks us to figure out where is it after, or at 0, 1, 2, 3, 4 seconds, and so on. So we are going to examine this, as we will with all two-dimensional projectiles, as two one-dimensional situations. We'll start out by looking at the horizontal part of the motion. Now, as we discussed, the horizontal motion of a projectile is constant velocity, and therefore there's only the one constant velocity equation to use. As we just discussed, the initial horizontal position is 0. So plug in our horizontal velocity. And by the way, I could write this as Vox or Vx. It really doesn't matter because it's constant. And then we can just plug in our times. 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. Now, really, you probably don't even need to write down an equation. If you just think about what does it mean to move constantly 25 meters per second, it means every second you go 25 meters. So your initial position is 0, and then 1 second later it's 25, and 2 seconds it's 50 meters, and then 75 meters, and 100 meters, and so on. On the other hand, the vertical motion of a projectile is a little harder to just think through. This is why we need to use the equations as guides for thinking. In this case, we may want to use the third kinematic equation, which says that the vertical displacement is equal to the initial vertical velocity times the time, plus 1/2 the acceleration times the time squared. Now, since we shot this thing horizontally, it had no initial vertical velocity, and anything times 0 is 0, so that whole term disappears. Add the initial position, vertical position, to both sides, and we get an equation to find the final vertical position at any time t. Plug in our initial vertical position and our free fall acceleration, and then we can just plug in the various times. Notice here you need the negative because you need this term to be negative so that it subtracts off of 90. 90 is your highest point. Right? As you fall, you're going to get lower and lower, so you need that negative in there. If If you leave the negative off, you'll end up adding, and it'll look like you're going up when leaving the building, which would be quite the trick. So when you punch in your various times, these are the values you get for your horizontal and vertical position. So back on our graph, this is a graph of height or vertical position versus horizontal position. This is like the movie in Logger Pro, all right? Not one of the time graphs. It's an actual path of the projectile. It's, in other words, a two-dimensional motion map. So if we graph our points, at 0 time, we're at 0, 90. Then we're at 25, 85.1, 50, 70.4, 75, 45.9, and 100, 11.6. Notice the shape. It's a parabola. Well, it's at least half the parabola. You don't get the full one because we shot it off horizontally, but it's parabolic in nature, showing you that you can look at projectile, two-dimensional projectile motion as a combination of constant velocity horizontally and uniformly accelerated motion vertically. Now, we can also use this to actually draw a motion map. I mean, we already have part of the motion map here. We've got dots at equal intervals of time to show the position of our two-dimensional projectile. So on that now, we just need to add velocity. Now, we're not going to draw a single velocity arrow. We could, but I would prefer to look at it as horizontal and vertical. So we're going to draw separate arrows for the horizontal velocity and then one for the vertical velocity. So what's special about the horizontal velocity of a projectile? Well, hopefully you realize it's constant. And it's constant 25 meters per second. So on our first dot, there's our Vx. On our second dot, there's our Vx. And you notice it's exactly the same size. And the same size there, and there, and there. So that's showing that the horizontal velocity is constant. Also notice the separation horizontally between dots is exactly the same distance each time. Constant velocity. Now, we're also going to draw an arrow for the vertical velocity of the projectile. Be a little careful here. At 0 time, what was the initial vertical velocity? It was 0. So there is no vertical velocity arrow on the first dot. However, on the second dot, now it's moving vertically, although slowly. So it's a small arrow. On the next dot, it's moving faster vertically. So a longer arrow, and then faster, and then faster. So notice your vertical acceleration, your vertical motion is uniformly accelerating. The velocity is getting faster and faster and faster, starting from 0. So this is kind of a motion map. Now, we could add an acceleration arrow if we wanted, although really it would just be a single arrow down that would be the same length for each one since it's uniform, but it kind of gets in the way, in my opinion. So I just want to draw the vertical and horizontal velocity arrows. So I hope this helped you understand a little bit more two-dimensional projectile motion with a horizontal initial velocity.